Okay, welcome to the second part of our second day of the quantum machine learning workshop. And Jacob, if you are ready, I think we can continue.
Thank you. Um, in the last session, as objective of the session says, we undertake a brave, hands-on, and independent exploration of hybrid quantum classical machine learning with the minimum of assistance. So what I'm going to do in this session is to introduce the concept. There'll be two completely different parts of it. So number one will be we'll take off from where we stopped in the previous session. We're working on automobile risk prediction. And we're going to, we try to apply a proper structure to it. That means we're going to apply a sigmoid function, which will make working with binomial outcome much easier. And that will require a lot of changes throughout the code. And you'll see why, because as you're going to look for the solutions, you're going to get errors. So hopefully we'll have a lively discussion here on the chat. But first, I'm going to introduce the concept, which hopefully will be part of the challenge. A lot of you will quickly finish that first component of extending the model which we worked on before and moved into exciting model in which the hybrid quantum classical component makes a lot of sense, because this is where quantum component actually gives a lot of value. So we'll talk about that. So let's get into it. It goes straight into here. Okay. So when we talk about hybrid quantum classical components, we're going to use a very simple logistic regression to start with. That's what we worked on. This is where the presence of quantum model is not really justified. Your classical model is going to work better. And it's always a question for me, if you're going to plug in a quantum component, there must be a good reason for that. And the good reason is obvious if you do things like quantum chemical simulations, because if you want to simulate it classically, the complexity is too high. So in here, and in this particular case, the data is very tiny, the model is very tiny. Really, why are we putting it in? And that's always a good test. If we're going to replace the quantum layer with classical layer, which model is going to work better? Okay, so it's always those questions. The data, if you work with hybrid Python, PyTorch penny models, you've learned already in the previous session. The data preparation, training and scoring is identical for both. What you need to keep in mind is that depending on your quantum model measurement, it will produce data in different dimension, and different values are going to be resulting from the measurement. So, for example, if you're going to do probabilistic measurement, you're going to expect 2 to the power of n of qubits of outcomes. If you're going to have the classical model, which is going to take the output of the quantum model, it has to be prepared to take so many inputs. The same thing with the input to the quantum layer. If the classical model is going to put some data in, it has to map your encoding strategy. So whatever data the previous layer generates, the quantum model needs to be able to absorb it. So that's keep it in mind. There must be consistency, like in any other neural network structure. It's not difference. In fact, it's getting very complicated if you do quantum convolutional neural networks and you try to fit your quantum model to act appropriately. You need to start calculating layers and so on. So it's really difficult for the quantum convolutional neural network to fit into the model like this. I mentioned that a moment ago. Ensure the quantum layer actually adds value to the classical neural network model. And test hybrid model performance against pure classical models and pure quantum models. It's not necessarily that hybrid model is going to be better than either of them. It's not going to be necessary that the pure quantum model is going to compete at all. So while it's all exciting and fun, unfortunately at this stage, the QML is not necessarily always giving you an advantage. Okay, so where it's going to help whenever we could take advantage of the large multidimensional Hilbert space that the quantum model is going to generate. And in some cases, this is exactly what other models need. So one of those models is a classical reservoir model, which works on the principle very similar to the kernel methods. So how kernels work? They take input data and they put into high dimensional, they do transformation high dimensions. And in this high dimensional space, the data is linearly separable. And the only problem with kernel methods is that you have to know which kernel method to apply. And classical reservoir models, then they don't worry about it. And we're going to talk about it in a second. So it's very interesting situation. This is where this high dimensionality of Hilbert space that the quantum model operate in is going to help. What you see on the right-hand side is what you've been working on. It's nothing new. And before we get into the practical part, let me just quickly talk about the reservoir computing very, very briefly, and I can demonstrate it in my demo. So most of the time is going to be spent rather than talking. You're going to work on the two tasks. So what's reservoir computing? Reservoir computing models are derived from recurrent neural networks. So they really apply to time series, the temporal data. And they utilize the concept of a reservoir. What is it? It's a large, sparse neural network, which is not being trained. It's randomly initialized with fixed weights. So that's a bizarre situation. But if it's a large and very sparse, it will transform input into some higher dimensional space. Are we training it? No. We just need to observe some of the constraints of how to generate those fixed weights, and it will does the task. So if you have small dimensional input, high dimensional output, it will do the job. Okay. So what happens after the input gets transformed into high dimensional space? Then we could apply a very simple linear model. It's called readout layer. It's like ridge regression. So in ridge regression, does not need a lot of training. It will apply instantly a separated data. So that's the principle of the workings. One issue with the reservoir, the classical reservoir, is that it should be able to echo the data. It should have the memory. You should retain information about past inputs for a short period of time, and should also have so-called memory leakage. Should be forgetting about the data it saw a while ago. And that's the hardest part of the reservoir computing, is to organize the memory leakage. So what we see here on the right-hand side below, that's a classical hybrid reservoir model. We start with, sorry, this is actually hybrid. We look at the classical on the right-hand side. The reservoir needs to be initialized with fixed weights. So we have this high, very sparse neural network, large neural network, and we initialize it with random weights. Then what happens is that we collect inputs as they come through and we weigh them with so-called leakage rate. And so when the new data comes in, it's not weighed at all. It gets pushed into the stack. When the new data comes in, all the previous inputs get weighed by a small leakage rate. When the new comes in, they all get again weighed. And so what happens is the leakage rate gets accrued on top of previous applications. So the very old data, it will have very little weight attached to it. So it will be insignificant in this training, so-called training. So now what happens is that if we use this neural network, it's going to explode the input data into its output, which is multidimensional. And then we have a readout layer, which is a simple linear model here. And this is the only thing that gets trained. And the training, it's trivial. It's very quick because it's a regression model. Surprisingly, it works. Okay, so that's an interesting thing. And I'm going to give you a demo of both before we get into the task. Now, what happens with a quantum classical design? First of all, we have the quantum reservoir model is the first stage, where we start with state preparation. Then we have state evolution. So what happens is that we create a circuit where we have of not trainable parameters. So this is similar to what happens with the classical model. And what we do, we manipulate input data. So the reservoir consists of the input data with the leakage, and that's being applied multiple times. So the state of the reservoir maintains that fading memory. And what happens is that the quantum circuit is going to transform input data from small dimensions into, now the question is what? We could consider exploding data into the probability distribution. So then we have exponential distribution of output. That may not be appropriate. So normally what we do, we have a larger circuit, which will have measurements across many expectation values across qubits. So we could monitor the size of the output better than with probability distributions and exponential enlargement of dimensions. And then we have a small model, the classical model, which is identical to what we had before. So basically, we rely here on the quantum model ability to very efficiently change the dimensionality of input space. That's all there is to it, and you just need to see it working. So what I'm going to do, I'm going to give you a little demo. So we have here, this is your challenge. So first we start with a classical reservoir model. And I'm going to prepare some data. So I'm using something called, by the way, today I was updating the version of this. It doesn't really matter if you use the old one or the new one. I just wanted to get more chaotic input. I was trying to fix the quantum model to improve it a little bit. So this is the data is a time series. It's a Mackie glass chaotic time series. It's a generator, a simple generator. And we're going to somehow, first of all, we're going to convert it into a sliding window. So create pairs. So we put this through, and we're going to split it into sliding window by 1 into pairs of window versus the next value. So this data was probably 2,000 items, and here we have training data is 990 examples of window of size 10, and we have one value which we want to predict, which is the next value in the window. Are you familiar with a sliding window protocol for time series? Hopefully. So basically, the time series is all the data, and the windows of 10 is sliding slowly forward. And for each 10 values, we want to predict the next one afterwards. So we have testing data, which is the remaining data, 323, also of size 10, and we have one value we want to predict. So if we want to look at the data, we just look at the Y's. So this is coming from the test data only. So this is the time series that we consider for the analysis and prediction. So we're going to develop this reservoir. So the reservoir will have a size of 100 inputs, or states, I should say. And those states will be accumulated and used in the process of prediction. And the reservoir itself, you can see we initialize it completely with random values. So this is the weights of the input reservoir. It's actually, this is the input weights. Sorry. So the reservoir weights are here. And basically, they're completely random. So they're fixed forever. So nothing is going to be changing here. We're scaling those values using the maximum eigenvalue of the big matrix that this represents. I'm not getting into mathematics of it. You could easily find a paper on classical reservoir with all the mathematics explained. Okay, so how we train it? We train it by accumulating states and applying the leakage. So this is the dynamics of the reservoir, is that you are going to take two components of the state. So the one component is the memory, which is the reservoir state. And the second component is the input. Oh, sorry, this is the input state, component of input state. So that's a leakage applied to input. So the input gets aged slowly. And this is the component of the previous memory. Okay, so together they will form the new state of the reservoir. Okay, I'm not going to explain exactly how it works, okay? And the training involves preparing the readout, which is the ridge regression. And so the ridge regression is basically applied here. So this is the actual, what happens if you take the ridge regression and you try to solve it for the state of the reservoir, you're going to get this formula. Okay, so this formula, it's a solution to the ridge regression equation. So this calculates the output. And then we could run predictions. I'm not explaining it well, I understand. You just remember the concept of it. So basically the prediction is for all input available. So test input is the entire 300 records of windows. And as we go through the input, we use the state of the reservoir to predict the values. So here's the reservoir state, which is coming from the update. So the reservoir is actually working on the reservoir state and changing its state, and it's applying it to calculate predictions. So that actually simulates the aging of all outputs, because in this series of inputs, we have some new ones and some old ones. So when we update the reservoir with time and we apply the new input, um, the outputs at the end are going to get smallest perturbation that the inputs at the very over old ones. Okay, so this is the simulation of aging of the reservoir memory when it applies the model to the data on input. So now we're going to get into testing of it. So first we're going to initialize the reservoir with random weights. It's done. We're going to train the reservoir. And the training involves basically creating a stack of old inputs with leakage. And we get prediction straight away. So this is training and prediction. And you can see it's a perfect match. So it's quite interesting because by exploding the data from lower dimensions to higher dimension, then we apply a very, very simple linear model which is trained instantly to fit the data in a high dimensional space. We could do this experiment to find out what level of leakage is best for this model and the data. So basically, I'm going through different rates of leakage to see which one is most applicable. It happens instantly, and you can see that for this data, so when the rate is high, it means the model does not care about all data at all. It pays more attention to input than its memory. Okay, so it depends on, I can see that at the end, this is a pretty good match, but somewhere in the middle, when the leakage rate was 0.4, that was the lowest possible mean square error. So the best model is somewhere in between here. And we're going to see this in the plots. Maybe we're going to see it. 0.4 is somewhere here. How we have to find it where it is. It's probably, okay, I shifted it incorrectly here. I should see more. Xlim is somewhere 0.4, 0.5, 0.7. Okay, I can just make it 0.7 here and maybe see it clearer. 0.7. Oh, somewhere here is the best leakage rate. Okay, so and it's interesting. The fitting of the data is perfect, and the data does not have. It is chaotic. It doesn't have a lot of repeating patterns, so it's amazing that it's such a good fit in a classical approach. Now, when we move to the quantum approach, we are facing a number of problems. Okay. In a quantum issue, so first of all, I'm just setting it up. Hang on, I'm doing something wrong. I have to open my quantum model. Sorry about that. I thought I had it open before. Advanced Challenge Quantum Reservoir. Okay. It's a bit different. It's the same data as before and the same test data. First of all, we are not working here with a physical reservoir of states. We're going to rely on the circuit and the circuit state to simulate the reservoir behavior. So what we're going to do is that we're going to have 4 qubits is the number of qubits in the reservoir, and it will determine how many outputs I want to have. I'm going to use the measurement in all directions, X, Y, and Z. So I'm going to get dimensionality of 12 and 2 layers of it's a very simple circuit. What happened before is that the leakage was recorded differently. It was recorded in the state of the big matrix that was being created. And here we actually don't have that physical matrix. So we're going to encode the leakage only in the input data rather than in state externally maintained. So we have here, so normally we have the component of the leakage which is applied to input and the component which is applied to the state. However, in our case, I'm going to encode both components of leakage to the rotation of the circuit. So here the leakage is combined from the input and the state into the qubit rotation of the circuit. So that happens for every single qubit. And basically, I am creating the circuit where the memory loss is encoded in the rotation, in the fixed rotation of it. And then I have reservoir dynamics. Oh, sorry, there's fixed weights in here. This is what this is the encoding of data that will come through the input. What it returns is the polys X, Y, and Z for every qubit. So since we have 4, I'm expanding the dimensionality from 10 values on input into 12 values on output. We could increase it, but let's just start with something simple. And I create a circuit here. So this is the training of the reservoir, which is similar to what we saw before, except that now it's slightly different because it's a very similar structure, but the mathematics of it is similar. We deal with observable. So this is 3 observables per qubit. And basically, the training is similar and the result is very similar, except that we lose one component of it because now everything happens within the circuit. And here's the prediction. Now, what's going to happen in testing is we're still going to train the reservoir with a lot of additional parameters in terms of number of layers, qubits. We specify the leakage rate. And this is the lambda regularization for our linear model at the end, which is the regression. Of course, we work on the simulator, so it will take some time. It happened already, and we could plot what happened at the end. It's nowhere near as good as the classical one, but you can see that somehow that circuit is simulating the memory loss over time, and it does some fit. However, what we don't know is whether it's actually the best fit, whether the leakage rate I put in there is appropriate. So I have here a number of different leakage rates to test which one is most appropriate for this. It will take some time. So I'm going to tell you something about the solution here. You can see the training here. I have this reservoir training, which has this epochs around. Why do we have epochs over something which doesn't get trained? So what happens here is that when we execute the reservoir on a state vector simulator, which works on the assumption that it understands statistical distribution of possible outcomes from the circuit. Every time I'm going to run it, I'm going to have the same statistical distribution and output. But if we run that on a real quantum machine, we're going to have quantum effects, which will influence measurements on the circuit on the qubits. So each time I'm going to run it, I'm going to have quantum randomness that is going to come into play. And so those epochs are used here to collect different types of measurements from the reservoir circuits and then average the result. So if we have normally with state vector, I can run it only once, and it will give me the result, which will be repeated every time. So there's no sense of measuring again. But if we're running on a real machine, this will soften up that level of randomness if we repeat the measurement multiple times. Okay, so with leakage examples, we actually have interesting results. It's similar to what happened classically, that at the end we have a good result, and somewhere in the middle we had some probably pretty good results. But it's very clear that this actually slightly misleading because I'm using smoothing here, but the lowest value is the very end. So that's actually, I could not actually get much different result by using different random seed. If we try to run it without a random seed, sometimes it shifts around, but there's a preference for the end. What it means is that the quantum model ignores the past and remembers only the recent data. Why is that happening? It happens for two reasons. First of all, because of the measurement collapses the state. So we have some nonlinearity in the middle, which perhaps it accelerates learning and forgetfulness of the model. So if we apply some leakage in the middle, the model on its own already forgotten some information. So that's probably what was happening here. There's a preference for most recent version and forgetting of the past. It can be improved. If you get this code, you may want to figure out how to improve it so that it relies more on the past memory rather than immediate memory before. So what is this memory? Is the window far away from the present. So if you look at a time series, we have very old windows and we have very recent windows. The whole idea of leakage is so that when you train the model, it's more influenced by recent data than the old data. So that's what happens with the reservoir computing. What I give you this challenge for is there is some solution here, and you may or may not fully understand and grasp it, but wouldn't be interesting to put it into the structure of PyTorch class. So in this way, that particular solution could be embedded in a PyTorch structure, and perhaps the structure of the reservoir versus the linear regression can be set as layers of the quantum structure. But that's a challenge. So I don't expect you to do this as part of the exercise today. So what I'm going to do today for this session is to start where we ended in the previous session. And that means we're going to explore the model we worked through a moment ago. So we use exactly the same data of cars. And this is a quick transformation of everything. So it's all done in 2 steps. But yeah, we do all the shuffling and selecting numeric values and eliminate missing values and scaling it. So this is done very quickly, and we get binary outcome. We reduce dimensionality. We apply PCA straight away. And we select as a model. So we are at the model development. Okay, I set margin to 0 for some reason. I don't know why. And data preparation for quantum modeling. And the model, the shape, and here it is, logistic regression. So what happened with this model so far is that we were using the result of the quantum model in its purest form. So whatever came from the measurement, we output it. If we repeated many times, we would have a frequency distribution between one class versus the other class. And even though this is the binary outcome, we treated it as if it was a numerical outcome. And that is a problem because if you look at um, the data is between 0 and 1. That's what we expect. But the frequency line is going to crisscross those two lines. So it's much harder for the optimizer to fit that line in between 0 and 1 outcome as we expect on output. So what we need to do is to apply some kind of a transformation at the end. In fact, we know exactly which one to use. We should be using a sigmoid transformation, which will fit the result to the required output. That means either 0 or 1 should appear on output. The problem is that it may not work well. So this will be the task for the rest of the time, because some of you will finish the task quickly. Some of you will perhaps move into the challenges. So we'll be here to help you, but this is what is the objective. Can we actually put the sigmoid function here? And if not, why not? And what needs to be changed? Also, I gave you here the Easter egg layer. I gave you a structure of a linear model, a quantum neural network, sorry, classical neural network, which actually uses the quantum model at the end. Can it be done? And if not, what needs to be changed about it? So you have us to help you, but this will be probably a challenging thing for you to do. So initially, I assume we just work with a single layer, but at some point, I want you to switch to that initially the additional structure. So we have 2 layers only, and perhaps include the Easter egg layer. So we have a richer structure. See which one works best. Okay, go for it. We have a lot more time than the last time. Obviously, the thing will be, what happens when you run forward? Oh, I didn't think it's going to run forward. It wasn't supposed to happen like this. It was supposed to crash. Okay. Um, okay, so it seemed to work. I was expecting we would get negative value out and it would give us a problem. Also note how quickly it was. But the challenge will be, I give you a challenge here. Can you change the measurement from, unless I've done it here already, can you change the measurement in the model? Instead of expectation value to return probabilities. In fact, I was expecting to get an error because expectation value is going to return values -1 and 1. And in the past, I had some problem with this. It would generate errors at the sigmoid function. For some reason, that disappeared. But The next challenge is, can you change the way we measure this model at the end, so that instead of returning expectation value, can we return the probability as an outcome? Because that will require a bit of work. We're real lucky here. Okay. Okay, so let's see how you go with that. What would be required? What would happen if we change expectation value to probability? With probability, we're going to get as many outcomes as measurements to the power of measurements as outcomes. It's a single qubit. We put the measurement on, we're going to get two outcomes. If you do expectation value, we get one outcome. Are you all sitting in front of a computer working? Hands up. Who is trying to do this work? Two people. Okay. Okay. Looks like all the people at the top. Yes, so we have now 5 people are working. The rest are listening. Okay. If you're having, if you want to ask questions, please do. I mean, the simplest thing is, what happens with this? I change this measurement now, and I try to train the model. I get an error. So why do we get an error? So the error is happening at model training. It says, I cannot deal with two elements. The output of the model has two outputs instead of one. Yes, expects one value versus two. Yes. So by putting probability as the measurement, we suddenly generate probability distribution of two possible values. So 0 and 1. So if you run it multiple times, you get in 2 bars. This is now what this function returns. Now, logistic regression function here, it expects one value at the end. Okay, so sigmoid function wants to get a single value, not two. The model generates two values. What can we do to get a single value past the sigmoid function? Any idea? So I have now a model which is sequential, consisting of a single layer here, which is the quantum layer. It returns two values. Somehow those two values should become one value. Any idea? What can we do? Yeah, so we add a new linear model. In fact, it's here already. Okay. So what we're going to do is to uncomment this, comment this out. So we're going to create an additional layer. We call it 5. And so we're going to have a quantum layer 1. It returns 2 values. We're going to add a new layer which takes 2 inputs and generates 1 output. And this is what we're going to wrap around in the sequential structure of a neural network. And hopefully that will give us a single result that the sigmoid function could apply to and squash it. So it fits nicely between expected outcome of 0 and 1. Make sense? Okay. So Prahlad has a hand up. No? Okay. So let's see what we get when you run it. Nothing changed so far because we didn't affect the quantum model. The closure I'll explain later. We trained the model to function the same. The training loop, it finished instantly. Okay, so that's actually interesting. So normally when this happens, we are waiting for those steps to appear one at a time. And here we run 100 iterations in 3 seconds. Why is that so? That's because we have a better fit between what's expected on output and the model. So PyTorch got exceedingly efficient now because the fit is actually perfectly matching what is expected. So we don't have a discrepancy between the linear fit and nonlinear fit for binary outcome. Okay, so we can also play here with different cost functions. We're using mean square error loss, but now we could actually apply different loss for binary outcomes. So that could be even faster. Okay, it's again 3 seconds, 84% accuracy. Okay, so this is for task 3, can we use BC loss like cost? Yeah, that's what we do. I've just done it, yes. BC loss cost function. Yeah, so this is, and yeah, that's exactly what it is. So that's actually a function which is specifically suited for sigmoid transformation at the end. But before we use mean square error loss, which is more for the linear outcomes at the end. But it worked. It worked well. We also have another, the softmax derived probabilities. It's an LLL loss. And that would be useful if you want to have multinomial results, okay, which I'm not going to cover here. We also have here other type of optimization function, which is the LBFGS, which I forgot what it stands for, but we could check it out. It's actually incredibly efficient. What is this? It's it doesn't want to say. Oh well, we know it's LB. Someone got the result? I'll say no. So what's going to happen is that this is the optimization function, which has its own internal loop. And this is an interesting situation because when you pass in the parameters to any other optimizer, you just pass the parameters like what are the parameters, learning rate, and so on. Since this optimizer has its own internal loop, that own internal loop has to have other information. So what other information you need to pass into it? We need to pass here the the closure. Why don't we have a closure here? And the closure is defined here. What is it? It's a function which we need to actually make the closure, and you need to, so this is a factory function. The factory function which will tell the small function closure what is the data we're training on, what is the model we're training on, what is the optimizer we use it, what's the loss function. None of that is known with a normal standard optimizer because it's not needed. All of that is, the training loop is guided by the optimizer independently of the optimization function using just the cost function. Now this will require the closure, and the closure needs to be written here somewhere. So make closure. Oh, sorry, the closure will be not here, but sorry, got it wrong here. It's already done. Okay. So the closure will be passed to the training model as a closure. If it's done with things like Adam and other optimizers, it was going to be ignored. But this will require it. So if you look at the training loop, which is here, and we pass the closure, if the closure is not none, the start point, the step will be utilizing the closure with additional information about what is the data, what is the optimizer, what is the other things, and so on. It will be driving internal loop of LGBFS. So what it means is now that we need to use fewer epochs because it's got its own internal epoch. I'm going to do it very quickly here. Epochs, number of epochs. I'll just change it here quickly. Let's see what we get. So now we get accuracy 91%. This is a fantastic optimizer. It gives brilliant results. So I'm showing it here because many people get stung by the closure thing. The closure is not described well in PyTorch, and its structure is not described well at all. You have to hunt on some GitHubs to find out how to use the closure. So here I give you the structure of the closure. It's a factory which will make closure. You pass the data, the model, optimize the loss function, everything that internal loop of this particular optimizer will require, which is not normally passed into the optimizer. Okay, and this is just a mini loop of steps taken in a normal training loop, but this is actually the internal training loop of this optimizer. So now I actually got not only a good model, I have a fantastic model. But slightly overtrained. Okay, so we got a good result on training, but we didn't get a good result on tests. And that's actually a lesson for everybody. Just because we could drive the training of the model to its depth and fantastic training result, we lost something in the process, and that means generalizability of the model. So now we get what we get normally with classical models. They overtrain very quickly on small data. And in here, it just overtrained very quickly. So we thought, yep, we never had accuracy at this level. The testing accuracy dropped. But it's always good to remember there is this option of this other optimizer. Um, it's often gives you, it saves you many times over. Okay, we are 10 minutes away from finishing. So that was one of the tasks that we did. It was to apply LBGT. Sorry, it's not here. LBFGS as a challenge task, but we've done it here. Good idea. Can you actually try to use the Easter egg surprise within the logistic regression model? So we have this additional function which generates layers. We could go back to the previous optimizer like Adam, because with this new fantastic optimizer, we overtrained the whole network very, very quickly. Think, how can we use the structure which is presented here, the Easter egg layers? Can that be used in some way in this structure to have a more complex sequence of layers, which could perhaps improve the result, and especially generalizability, or if we're going to get even worse and we're going to overtrain it beyond all help. So we're dealing here with a very tiny data. So now when we have the model, we have the model which trains very quickly, very efficiently because of the sigmoid transformation at the end. Maybe it's time to also play with the quantum model itself and its structure. Maybe it's also time to get much larger data rather than limiting yourself to very tiny data, which normally is suitable for a quantum model. We have actually have a strategy to push quantum models to solve real problems because we gain efficiency from that hybrid interaction. Now, would Easter egg layers work? A limited memory burden, Fletcher, Gottfab, Shanghai. Yeah. Task 4, got BC 0.35. Yes, that's not good, right? We have 7 minutes to go. It should be very simple with
Oh,
that. Yeah.
Jacob, actually, we have 37 minutes.
Oh,
If you want,
37.
yeah, yeah. Mhm.
Ah,
No worries.
thank you.
You can
That's
take
good.
time.
Thank you. Thank you, Pavel. I'm just I'm getting confused with my clock. Okay, because I know we work out of in different time zones. So okay, so which is good. So let's try to put here the Easter eggs. What should we change here? Any ideas? So the Easter egg generates lots of layers here. It puts them, I think this one is not needed here because it's not included. But perhaps I could use it. Maybe here I could use that model because that will convert, that generates 2 items, that converts it to 1. So we don't need that here anymore. So that will receive, oops, and this one as well. We need to create a new call here. So layers, very cool. Easter egg. And that may be it. Okay, Easter egg layer not defined. I need to pass self probably. It's a local function. So we have here again superb accuracy, but let's see what is the test accuracy of this solution. So again, we see what we saw a moment ago. The model overtrained very quickly. The training continues and still has ability to train further, but it finished training. At this point, we started losing test accuracy. So that is it's a problem with small data sets. And it's also a problem of using a quantum layer. What if we simply remove that layer? Would it work? We would have to match the mapping between, if we skip it, let's say we skip from, we need to get one outcome. Let's say we have a model like this. Would that work? So we have model ReLU 3, and then we need to have Lin 5 at the end. If we have just classical solution, would that give us better result? I think that somewhere there, okay. Try to fix it for me. I'm using, it doesn't like me generating quantum layer. What error do I get? Draw circuit. Of course, I can't draw the circuit because we don't use the quantum layer anymore. I could try to generate it just so that we have the circuit. Here model, where do I save it? I don't save it anywhere. Maybe just reduce the epochs. And it's well, there's a different problem. Yeah. So I should be able to create that model and save it somewhere. I need to call QLayer. Yes. Okay. So I just call it so that we could save the circuit so we don't get an error. But we're not going to use the circuit. We're going to skip it. Now we have a completely classical solution. Score it. And it's actually better than before. So what happened was, okay, the training performance on uh, the cost was ridiculous. It's still bad, but the accuracy improved. So classical model works better than hybrid model. And that's common. So it's always good to do a test like this. When you embed a quantum model and you think, yep, we added layers of classical layers and says, yeah, we improve it. So we have a better quantum model. No, it's the quantum model which spoils the working of the classical model. And that's very common. Okay. Okay, I would like to give you some time to work on other things. For example, unfortunately, that you'd like to see some demos rather than working on it. What else we can work with this? There was another task here. We've done this. We included the Easter egg. In fact, that model is too complex. We could probably improve it by removing ReLUs from it. It would perhaps slightly improve the result. It doesn't make sense to include more epochs because it overtrains already. Let me try to cut down on the complexity of the classical model. And let's say we get rid of all of the ReLUs. So leave it only linear. I actually found that that actually improved it a little bit. So we get rid of this ReLU and this ReLU. So normally it's a good thing. We slightly improved it almost 80%, but we had better results with pure quantum model. Okay, so so that's actually interesting. We toss it up because here we have competing with a classical solution which we know works exceedingly well, and our data set is very small and very poor. So it's only like 300 records in this data set. So you can see here that the classical model overtrains straight away, but the data is complex enough so that it doesn't memorize it, or it memorizes too much. So that's why we have here the cost is, it doesn't matter as so low, but it instantly is right. And we can see here that the accuracy, it stops early. So this is not always hybrid solutions are going to give you the benefit. Sometimes it's better to stick to the classical only or quantum only, but we have this option. Now, do you have any questions? Reduce the epochs. Yeah, we could reduce the epochs to 3, and we're going to have the same problem because it overtrains very quickly. It has enough capacity to overtrain. Have a look how big is are those layers which we included here. We have 4,500 parameters versus about 80 parameters in a quantum model. So we're looking here at a massive model. If we started reducing the parameters, it would work better. So if we say 8, maybe 16, or less is often much, much richer. Now it's still too complicated, but it's slight improvement in the results. Okay, so the data is too poor for the solution. Training in batches. Not for this data. It's not enough data here to create batches. One thing about definitely when you have a decent size data set, it's better to train in batches, so that you need to have a decent size batch where the training occurs on small number of records, and you can do it especially for GPU, so that you could load your data to GPU in batches, and the training could be happening on a small subset of your training data, which fits into GPU. And what happens is, in such a case, that you get only training component in the batch, and when you apply your test, you could actually do the test on the test data at the end of the batch, so you could actually maintain your training performance and test performance at the same time when you're training in batches. Okay, so I don't think it makes much sense if the data is too poor. We would have to step out and start loading a larger data sets, because now we have a method of doing it by combining it with the classical layers. Okay, now when it comes to the challenge, are there any data sets that works better with quantum models than classical models always? Yes, not the data sets that I think that the free data sets are very small. It'll be good to find out. You need to find a problem which has a quantum component in it. So either the problem where you could quantize your data somehow, so that the data could already start with some distribution, probability distribution, or data that you could fuzzify. So I'm currently working on the project that we're looking at a time series, and every point in the time series could be represented as a distribution of possible values. So that already feels like a quantum effect of some kind of a representation of the data itself has a quantum nature. With Sebastian, we're working on graph applications where we try to represent graphs in a quantum mechanical way. And that already starts with a quantum representation. Okay, so really we need to look at problems where the problem statement itself fits the nature, the quantum nature. If we start with a very classical data and a classical problem, we're not going to gain a lot of benefit from the quantum modeling as such. That's why in chemistry, quantum chemistry works very well, because the phenomena we are trying to model are actually quantum phenomena. Power of data and quantum machine learning. Okay, so we've got some example that Thomas provided. Am I still in sharing the screen?
Yes, we can see it.
Ah, because my bar disappeared from here. So I thought, oh, it appeared on my another screen for some reason. So anyway, so somehow I got screens remapped and moved around. I don't know why. And sorry about that. Okay. Okay, since the challenge here will be for you, see if you could embed this quantum reservoir into the PyTorch structure. You could do it in your free time. When it comes to the quiz, I am looking at, we are looking at testing you on the subject matter covered in presentations and hands-on exercises, so the demos. Some of the work which has not been covered in those demos, but we're fitting into the compulsory part, that's also going to be tested. So look at the tasks associated with every notebook at the top. And normally I say things like complete the unfinished task. They should belong to the top. And we're going to ask questions about what you're going to normally find out in the process of doing those tasks. So there'll be a quiz available, Pavel, from tomorrow, or?
You mean the quizzes, right? Actually, we haven't decided, so we'll try to
Okay.
publish them
Yeah,
as
yeah.
soon as possible,
We
but
need,
we need
yeah,
to
yeah.
review them. Mhm.
Yeah, okay. So in the next few days, the test will be released and you could complete it in a week or 2 times. So that actually takes us to the end. We have covered quite a lot. There will be benefit for people who come from the quantum computing area and people from machine learning area. Hopefully, you found something useful for you yourself, whether you enrich yourself with machine learning or the quantum machine learning. We covered simple aspects like fitting sign function. I try to emphasize the importance of preliminary steps in data preparation and data encoding. Um, the models which we used were very, very simple. They didn't have much internal structure when it comes to the ansatz. But we could always create custom models like which they funneling out and funneling in. A little bit what happens with the traditional classical neural networks. We talked about the complexity of measurement. If you measure too many qubits, we're going to have a lot of outcomes, especially if your measurement is probabilistic, because every measurement doubles the number of outcomes. If we measure the expectation values, we have more control over the outcomes. And so we covered issues to do with estimation models. And today we covered the classification models. There's the whole layer of machine learning aspects in terms of interpretation of results, improving the results after training, like moving the threshold in the classification. And then today we also spent some time looking at integration between the classical models and quantum models, not always with is beneficial for the quantum model. Okay, so sometimes the quantum model is what spoils the result, but you need to find the right application. So, that's important for you. Some people who work in banking and finance, you're going to find that a lot of mathematics in finance is very similar to mathematics in quantum mechanics. Use similar maths in both. So you could take advantage of it, especially if you rely on generating like random paths, looking at like option movement in time. Those are good applications for quantum computing. If you simply look at getting a very simple quantum network, a neural network, and try to apply it to simple model, you're not going to get the benefit from that. So look at the complexity of the phenomena you try to model. This is where you're going to get the greatest benefit. But what it means for you personally, if you're moving into quantum machine learning, you should be focusing on developing skills in developing models, fitting data to it, generating outcomes, creating experimental frameworks to get a variety of different tests. tuning the models. All of this is universal and applicable to much more than simply um, complex models where you get quantum advantage. This is the training. Even if you develop a simple models, is something that everybody, the whole community learns. So it's worthwhile to be part of that community. We try to tap you and to get you into the PennyLane community. It's a vibrant community, a lot of very young people working in that, a lot of physicists. So unlike Qiskit community, which diversified into computer scientists, PennyLane is still full of physicists and mathematicians. So I noticed a lot of people are with a physics background, and you could find comfort that there's a lot of people like yourself. Um, I'm not a physicist. I'm not a mathematician. I'm a computer scientist. So if you are a computer scientist in heart, um, there is hope for you as well. It's a much harder work for computer scientists to break through to quantum computing and quantum machine learning. Um, but we have established some community here. So we had 200 people who started this course, and we still have 90 listening to me. Let's keep in touch because and perhaps through Q Poland we could establish the community of people who share ideas and share um, uh, outcomes, results of experiments, problems, and this way we could all learn and create better skills for ourselves and opportunities on the growing market of quantum computing and quantum machine learning. So that's probably the end of my presentation. Um, Thank you so much. Thank you to Pavel, who organized this. It's great to have colleagues who helped me to develop this course, and we have mentors who were busy answering your questions on different platforms. Let's keep in touch. Remember, we all have LinkedIn accounts, and perhaps we'll have a more advanced workshop in the future. Perhaps we have a more introductory workshop for some people who found that this was too hard, perhaps.
Mhm.
So, Pavel?
Yes, yes. So maybe I will say a few words at the end. So first of all, thank you, Jacob, for leading this workshop. That was a great workshop, definitely, and I can see that the comments from our participants are great. I would also like to thank all our mentors for a great job they have done before the workshop and during the workshop in answering the questions. And as you said, definitely. So now we'll soon stop the recording and we'll close the let's say the publicly available part here on the Zoom. But the discussions on Discord may continue, and especially as you said, we are going to send you the final test. So if someone would like to get a certificate and maybe also prove yourself to check if you what have you learned and what's your current stage, you can take the quizzes that we'll prepare. So we'll announce them within a few days, hopefully by tomorrow, but we'll see. And of course, there will be a video recording shared on Discord. There were many questions about the recording. So yes, we are planning to share the recording on Discord. And finally, the last thing regarding what Jacob said about QPoland. Indeed, QPoland is growing, so we are open, and we also invite people, especially people from Poland, to join QPoland. So other people can also follow our groups, our social media, join our QPoland's Discord server. But in order to organize the events, it's much easier if you are already here in Poland, or at least if you speak Polish, of course. Um, but as Jacob said, we can also think about organizing some subdivisions, some groups within Q Poland. I know that so at the beginning in the introductory talk, I said that in Q World we have 36 Q cousins worldwide, right? So Q Poland is just one of them. And for example, Q Turkey is very active in the field of creating some subgroups. They have something like study groups at different universities. So if you are affiliated at a university, like a university here in Poland, you can also think about organizing something like a students group where you can also work on similar educational materials. You can organize similar lectures. The materials are open. They're available in the repository that was shared by Jacob. And in Keyword, we have many other educational trainings, educational materials, which you can also use to organize similar workshops, similar courses in your local communities. So we highly encourage you to do it. And yeah, if you have any questions, please stay with us on the Discord, and we will be happy to answer them. It's possible that we'll not be that active in the next days, but we'll still stay at the Discord for several weeks at least, and later we'll archive the Discord. But for now, we still have the homeworks, the final tests to share. So thank you once again, and yeah, thanks to all the participants for staying with us. The interest was great. So I already posted that on LinkedIn that we've received about 750 applications, and we've invited more than 500 people. So yesterday in the peak there were more than 170 participants. So now we can see that we still have more than 80 people with us, which is great, and we are definitely planning to organize similar workshops in the future. So yeah,
Thank you.
thanks once again. Thanks everyone. So Jacob, can we stop recording now, or is there anything else you would like to add?
Sure.
Okay, so I will stop
Let's stop
recording
sharing.
now.